Hello students, before we go into today's topic, I want to give you a brief overview of what we will be covering in this lecture. Today, we will be exploring the overview of fresh properties of concrete, workability, segregation and bleeding in concrete, setting time of concrete, process of concrete manufacture and its compaction that sets the stage for understanding the various aspects of fresh concrete. The fresh concrete, it's often referred as plastic concrete, is a freshly mixed material capable of being molded into any desired shape. The proportions of cement, aggregate and water mixed together dictates the properties of concrete both in its wet and hardened state. Before dealing into the specifics of fresh concrete in this chapter, it is beneficial to understand the role of water in concrete making. The role of water. A minimum quantity of water is necessary for the complete chemical reactions with cement and occupying the required gel pores. Theoretically, water cement ratio required is 0.38. The ratio below this threshold may lead to incomplete hydration and insufficient space for gel development, which basically forms and gives the strength to the concrete mass. The water cement ratio adopted at the site must consider the presence of free surface moisture in the aggregates, both the coarse as well as in fine, and the absorption characteristics of the aggregates. Workability of fresh concrete. Achieving 100% compaction of concrete is crucial for attaining maximum strength, as lack of compaction results in air voids that can adversely affect both the strength and the durability of concrete. In order to ensure that the concrete is fully compacted with the available effort, a higher water cement ratio than that calculated theoretically may be necessary. The water also serves to lubricate the concrete, facilitating easier compaction and placement without the segregation or loss of homogeneity. If we want to go into a definition of workability, the workability refers to the ease with which concrete can be mixed, placed, compacted and finished. The different construction jobs require different levels of workability. For instance, the concrete considered workable for a mass concrete foundation may not be suitable for roof construction. Properly estimating the right workability based on experience and understanding can make the concrete operations more economical and durable. There are lot of factors that affect the workability. To name a few, number one, water content. A higher water content per cubic meter increases the fluidity of concrete, which is a crucial factor affecting workability. Second, mixed proportions. As we know, the concrete is formed by the different materials. The aggregate cement ratio significantly influences the workability. A lean concrete with higher aggregate cement ratio has less paste available for lubrication, resulting in lower workability, whereas a rich concrete with a lower aggregate cement ratio provides better workability due to more paste availability. Third is the size of aggregate. Larger aggregates have less surface area. Because the surface area is less, it will require less water for wetting and the less amount of paste needed for lubrication purpose, which is resulting in higher workability. Fourth point is the shape of the aggregate. The rounded aggregates offer better workability as compared to the angular or elongated or flaky aggregates because of reduced surface area and the frictional resistance. Fifth point affecting workability is the surface texture of aggregates. A aggregate which has a smooth rounded aggregates improve workability, whereas a rough textured aggregate reduces it because of the increased surface area. Sixth point is grading of aggregates. Well graded aggregates is going to result in minimum voids. These minimum voids offer better workability because of the availability of excess paste for the purpose of lubrication, thus making the mix cohesive and preventing the segregation. Seventh point is the use of admixtures. Admixtures, particularly the plasticizers, superplasticizers, greatly enhance the workability. Air entraining agents can also reduce internal friction and improve the mobility by acting as artificial fine aggregates. Measurement of workability. Now, workability as such is a complex property that is challenging to define the measure precisely. There are various tests which provide an information about the parameters related to workability. Most commonly used tests are: number 1, slump test. It is the most commonly used method for measuring the consistency of concrete. It is suitable for both lab as well as on the site. It is not ideal for very wet or dry concrete, but gives an indication of uniformity between batches. Number 2 method is compaction factor method. Measures the degree of compaction achievable with a given effort, more appropriate for low workability concrete. Next method of testing is the flow test. Flow test measures the flowability of concrete suitable for high workability concrete. Next test is key ball test. It measures the penetration of a steel ball into fresh concrete, providing an indication about workability. VB consistometer test. This measures the time required for a standard amount of concrete to change from conical shape to cylindrical shape because of the vibration. It is used for stiff mixes. The practical applications of workability test. Workability tests are essential for ensuring the consistency and quality of concrete. Workability provides valuable information for mix design and help detect variations in the quality of the concrete which is being formed under the different batches. By monitoring the workability, adjustments can be made to maintain the desired quality and performance of concrete. Despite their limitations, workability tests like the slump test are widely used due to their simplicity and practical utility. As I told that the slump test can be used in the lab as well as in the field because of ease in test. They help in controlling the quality of concrete on site and ensuring successful execution of construction projects. Manufacturing process of concrete. The process of manufacturing concrete involves several steps to ensure the desired quality and performance. Number 1 is batching. Batching is nothing but measuring the correct proportions of the components, that is the cement, aggregate, water and admixtures if required to be mixed. Second step is mixing. It is combining the materials in a mixer to achieve a uniform and homogeneous mix. The better mixing, better will be the quality of the concrete. Third is transporting, moving the concrete from the mixing site to the construction site using suitable transportation methods. Fifth is placing. It is nothing but pouring the concrete into the formwork or molds, ensuring that it reaches all the corners and edges. Fifth point is compacting, removing the air voids from the concrete using vibrators or other compaction methods to achieve maximum density and strength. A well compacted concrete gives the best strength. So, that is one of the targets of it. Sixth point is finishing, smoothing and leveling the surface of concrete to achieve the desired finish. Setting time of concrete. The setting time of concrete refers to the time it takes for fresh concrete to transition from a plastic state where it can be molded to the desired shape to a hardened state once it has been placed. The initial setting time is the period after which concrete starts to lose its plasticity, while the final setting time is when the concrete has completely set or hardened. There are lot of factors that affect the setting time. We will discuss one by one. Number 1 is the cement composition. Different types of cement are having different setting times. Rapid hardening cement sets faster than the ordinary Portland cement. So, that is very important about the composition of cement. Second point is the water content. Higher water content prolongs the setting time. Segregation in concrete. Segregation in concrete refers to separation of its constituent materials, that is the aggregate, sand, cement, leading to a non-uniform mixture. The ideal concrete is characterized by even distribution of all its ingredients, forming a cohesive and homogeneous blend. When a concrete sample demonstrates a tendency for components such as coarse aggregates to separate from the rest of the mixture, it is indicative of segregation. This phenomena comprises the strength and uniformity of the concrete, resulting in undesirable properties once it hardens. There are different causes and the types of segregation. We will deal by it one by one. The constituents of concrete vary significantly in size and specific gravity, contributing to their natural tendency to separate because of their different specific gravities. So, segregation can manifest in 3 primary ways. Number 1, coarse aggregate separation. The coarse aggregate settle or separate from the rest of the cement matrix. Second is paste or matrix separation. The cement paste or matrix that gets separated from the coarse aggregates. Third is water separation. Water being the least dense component of concrete making, it separates from the mixture. Now, how to prevent? So, for prevention of segregation, number 1 is concrete that is well designed, that is while deciding about what should be the different factors such as aggregate grading, size, shape, surface texture, coupled with optimum water content, forms a cohesive mixture resistant to segregation. The matrix cohesive and fatty properties prevent the aggregates from separating, while the aggregate in turn contained in the mix. Thirdly, the properly proportioned mixes with sufficient matrix and controlled water content exhibit minimum segregation tendencies. The factors which are favorable for segregation are several conditions that contribute to segregation in the concrete are: number 1, improper mix proportions, insufficient matrix to bind and contain the aggregates, that is the very first and the most important factor. Second is the excess water content. Overly wet mix tend to segregate more. Third is inadequate mixing. If the constituents are poorly mixed, we are going to have a poorly mixed concrete and that can segregate very easily. Thirdly, height of drop. When the concrete is placed, so we need to drop it from some height. The dropping concrete from significant heights such as during column or such locations, there the possibility of segregation is very much there. Equipments use issues. Discharging the concrete from poorly designed or worn out mixtures can cause segregation. Next is transport methods. Using conveyor belts, wheelbarrows, long distance hauling or lifting by skips and hoist, all these are going to lead towards segregation. The excessive vibration. Vibrating overly the wet mix or vibrating for extended periods than what it should be can cause the coarse aggregates to settle and leading to segregation. Now, what are the remedial measures? In order to mitigate the segregation, we need to adhere to proper mix proportions and handle, transport, place, compact and finish the concrete correctly. If segregation occurs, brief remixing can restore homogeneity. Using cohesive mixes with workability agents, pozzolanic materials and air entraining helps agents reduce segregation. The observations and measurement. Although challenging to quantify, segregation can be observed during concreting operations. The slump test or flow test patterns provide an insight into concrete quality concerning segregation. There is another very important term in concreting, it is bleeding. Bleeding or water gain is form of segregation where water rises to the surface of the concrete, being the lightest component. This phenomena is more pronounced in overly wet or excessively water concrete, poorly proportioned and inadequately mixed concrete, especially in thin members or during sunny weather conditions. The bleeding can be minimized by number 1, using appropriate water cement ratio. If excessive, then naturally it will have a tendency to bleed out or come to the surface. Second is incorporating fine materials like fly ash to improve the cohesion. Next, proper curing the concrete to prevent the rapid drying. Now, what are the effect or consequences of bleeding? Bleeding water accumulates on the surface, sometimes bringing cement along with, forming a weak layer which is called as latens. This layer compromises the wearing quality of surfaces like slabs and prevents leading to dust in dry conditions and mud in wet conditions. Additionally, latence increases shrinkage cracks and weakness, the bond between concrete layers. Bleeding channels and structural integrity. Excessive water cement ratios create continuous bleeding channels, increasing the permeability. Water intercepting aggregates forms voids, and that leads to weakness the bond between the aggregate and the paste. Similarly, water which is beneath the reinforcing bar reduces the bond strength between the reinforcement and the concrete. How to mitigate it? In order to mitigate the bleeding, revibration of concrete can improve the bonds affected by bleeding. Delayed finishing operation reduce the latence formation, which is the potential problem. So, proper mix proportions, complete mixing and the use of finely divided pozzolanic materials like fly ash or such and air entraining agents, they help minimize the bleeding. Finer cement or low alkali cement as well as rich mixes also reduce bleeding tendencies. Controlled bleeding. All the bleeding is not detrimental. If evaporation rates match the bleeding rates, it can benefit the concrete by removing excess water after it has provided required workability. Early bleeding is less harmful as the plastic concrete subsides and compacts. Delayed bleeding, however, can cause significant damage once the concrete has lost its plasticity. Testing for bleeding. The bleeding test measures the relative quantity of mixing water that bleeds from freshly mixed concrete. This involves using a cylindrical container, a tamping bar, a pipette and a graduated jar. The concrete is layered and tamped and the bleeding water is collected at intervals. The percentage of bleeding water is calculated by comparing the total quantity of bleeding water to the water content in the concrete sample. Compaction of concrete, the definition and the importance of it. Compaction of concrete involves the process of eliminating the entrapped air from concrete mix. During mixing, transporting and placing, air gets entrapped within the concrete. So, it is important that it should be removed. The level of entrapped air correlates with the workability of the concrete mix. Stiffer mixes contain more air and thus require greater compaction efforts compared to more workable mixes. The impact of entrapped air. The entrapped air significantly reduces the concrete strength. Example can be like 5% voids can decrease the strength by approximately 30%, while the 10% of air voids can reduce the strength of concrete to the tune of 50%. Achieving 100% compaction is crucial for maintaining the desired strength and durability of concrete. Poor compaction increases concrete permeability, allowing aggressive chemicals to penetrate and degrade both the concrete and affecting the reinforcement. Necessity for proper compaction. Full compaction ensures maximum density and strength with the compacting efforts typically available on construction sites. Although a mix with adequate workability is essential for compaction, the mix should not be overly wet as it can reduce the concrete strength. The aim is to compact the driest possible mix to achieve the maximum strength. The methods of concrete compaction. There are several methods that can be employed to compact the concrete, each suited to different conditions and the requirements. To start with, first category is hand compaction, and in that number 1 is rodding. It is achieved by using a rod to manually compact the concrete, often used for very small jobs or where mechanical compaction is not possible. Second is ramming. The manual ramming of concrete, which is typically used for compaction in footing and sub-base layers. Compaction by vibration, where the machines are being used. Number 1 is internal vibrator, which is also called as the needle vibrator. A vibrator inserted into the concrete to eliminate air pockets. This method is effective for compacting large and dense structures. Second is the formwork vibrator or external vibrator. These vibrators are attached to the formwork in which the concrete is being placed. This is useful for sections where internal vibration cannot be done. Next is table vibrator. This type of vibration is used for precast concrete production. The table vibrates and the molds to remove air. Next is platform vibrator, very much similar to table vibrators, but it is used on large platforms for various number of precast elements or members. Next is the surface vibrator or screed vibrator. Vibrators used on the surface of the concrete, and it is ideal for slabs and pavements. Next is the vibratory roller. This is primarily used for compacting large concrete surfaces like pavements, roads, slabs, etc. There are some other compaction methods also. Number 1 is compaction by pressure and jolting. This involves applying a large amount of pressure and jolts to compact the concrete. Commonly, it is used for the precast elements. Second is compaction by spinning. This utilizes the centrifugal force to compact the concrete. Often it is used in production of pipes and cylindrical structures. Ensuring quality in compaction. In order to achieve the optimal compaction, the following aspects must be considered. Number 1, workability. The concrete mix that we are making should have sufficient workability to allow easy compaction without being overly wet. Second is compaction equipment. A proper selection of the appropriate type of vibrator or compaction tool based on the specific job requirement is very essential. Compaction duration. Each compaction is having a particular duration. Adequate compaction time ensures air voids are being removed without over compaction. This otherwise could cause the segregation or other related issues. Addressing compaction challenges. The challenges such as access limitations, the mix design and environmental factors, for example, humidity, temperature, etc., must be managed effectively. For instance, compaction in hot weather may require different techniques requiring additional water management strategies to prevent the rapid drying and to ensure thorough compaction. Finishing operations. Finishing is the final step in the process of creating concrete structures. It is important to note that finishing is not universally applicable to all concrete operations. While concrete has historically been perceived as a common material with limited aesthetic appeal, advancements have significantly improved its surface finishes. Contemporary concrete can now achieve visually pleasing appearances and other attractive architectural effects. Categories of surface finishes. Surface finishes can be classified into basically two main categories. Number 1, formwork finish and applied finishes. Under formwork finish, this category involves finishes that are achieved through the use of different types of formwork or mold treatments that impact the texture and appearance of the concrete surface. Second is the applied finishes. These are finishes which are applied directly to the concrete surface after it has set, including techniques that modify or enhance the surface texture appearance. If we summarize the today's session, understanding and managing the properties of fresh concrete is very crucial for ensuring high quality outcomes in construction. Nowadays, lot many construction activities using the concrete is being done, where we require the different grades of concrete, and every concrete that is being made has some specific requirements. So, in order to ensure the quality of the concrete after finishing, we need to understand what are the properties and how the construction should be done. The key aspects in this include: number 1, optimizing water content. A proper quantity of water should be used, and that is defined by the water cement ratio. So, a proper water content is very essential. Second is workability, and to measure it. The workability is the ease with which the concrete can be formed and placed and finished. So, for that we need to have a proper measurement of the workability, that the concrete that is being developed will be useful for the purpose for which it has been made, and preventing the common problems or issues that we have discussed. It includes the segregation, that is the separation of the coarse aggregates, or the bleeding where the cement paste water comes out of it. So, we have seen what are the factors affecting the segregation or bleeding, and adhering to a rigorous manufacturing process. The proper manufacturing process must be followed the particular type of concrete. Advances in technology and techniques continue to improve the concrete compaction and finishing. We have discussed that although the concrete is made, but unless until it is properly compacted and finished, it is not going to serve the purpose. So, this is leading to more durable and aesthetically pleasing concrete structures, which is the main aim of the making a concrete. So, dear learners, this brings us to the end of today's lecture, and we have discussed at length what is concrete, the factors affecting workability, segregation, bleeding, how the proper placing techniques should be adopted. So, I trust you have gained a valuable insight. Thank you for your attention.